Good morning, everybody. Today we are going to talk about chapter number 8, Introduction to Gas and Vapor. Our agenda today is ideal gas. We will go through the overview of the ideal gas. Then we will cover the overview of the reciprocating engines, Otto cycle. Then we'll solve one example to understand the idea of the Otto. So the ideal cycle, which is talking about the reversible cycle as a Carnot cycle. We have explained everything regarding to the Carnot cycle from the previous chapters. But according to the Carnot cycle in this chapter, which is talking about the higher thermal or the highest thermal efficiency of the type of the whole engine because it is ideal, which is has no friction, has nothing could be affect the whole system, and the efficiency it could be reached to 100%. So the ideal cycle is about the cycle of the resembles of the actual cycle closely, but it's made up totally internal reversible process, where it has the efficiency that's related to the W net over the heat in, or it could be dividing by the mass of each part. Usually we have four process or four kind of point that will be the engine process is flowing from point number one to point number two, that we are increasing the temperature slightly, then we will move between two and three. At this part we will some heat inlet will be additional moving to the system. Then we are reducing in the temperature, but keeping the isentropy is similar. Then we are rejecting the type of the heat or the rest of the heat from the whole system. Then we are getting the W net based on the heat in negative with heat. While the idealization and simplification in the analysis of the power cycle, we have explained earlier that related to this ideal gas, there is no friction at all, which means there is nothing could be increase the temperature. In this part, there is no experience in the pressure drop. In the other part, there in the expansion and compression process, it will be as a cost equilibrium manner. Then this kind of the connecting for the system that could be well insulated, and the heat transfer through the this kind of the piping, it will be neglected. The overview of the reciprocating engines. Usually we have to understand the whole parts of this system. Usually we have cylinder covered in the top by two valves, one for the intake valve, the other one for the exhaust valve. The intake valve, it will be allow the gasoline or the fuel mixture to be inlet to the whole cylinder. Then the exhaust valve will allow the smoke to be released to the exhaust. Then inside the cylinder we have piston. This piston will be moved up and down based on the required of the revolution of the whole engine system. So when the piston is moving to the top, we will reach to the top dead center, and the bottom part we will reach to the bottom dead center. When it reaches to the top dead center, we here in this part we have the whole valve supposed to be closed. Then we have clearance volume. Why this clearance volume? Because usually we are releasing the whole exhaust, the whole smoke to the exhaust. And we have the bottom dead center. At this part, the piston will be moved down. Then we will get all the gasoline or the fuel mixture to be moved inside. So this part we will call the stroke. And at this part, we have the displacement volume. So the diameter of the piston, we will call it bore. So based on this, we will have to find the compression ratio. The compression ratio, it will be equals the maximum volume over the minimum volume. The maximum volume, as explained earlier, which is the displacement volume, that is the distance between the top dead center and the bottom dead center. Then the minimum volume, which is the clearance volume, which is at the top section of the when the piston is moving to the top part. Then the mean effective pressure. This one, it could be able or it will help us to calculate the W net over the volume maximum negative with the volume minimum. These two parts are very important in the solution or calculation. So you may take care of this kind of two formulas because both these formulas, it will help to calculate either the maximum volume or the minimum volume. And the other part, it will be calculate the mean effective pressure. Usually the mean effective pressure is the last part of your calculation that you need to calculate from the whole process of the engine. Then we have two types of the combustion. So the first one we have spark ignition, and the other one we have compression ignition. In the spark ignition, it's from the name, which means that we have a spark that is inside the system. This spark that comes from the plug when we have compress all the combustion inside the whole cylinder, then we need to get the spark from the plug to get the full combustion. Then it will be convert the whole gasoline to a fire that will force the piston to push down and rotate the crankshaft. The other part, which is the compression ignition. This one, it's about the air-fuel ratio that will be moved inside the whole system. It will be compressed up to reaching to the above the maximum of itself ignition temperature. Then this one, it will be applied in the diesel engine. So the Otto cycle, we have four strokes that will be moved inside the whole system. The first one, which is the air-fuel mixture to be inlet from the inlet valve, then the piston will be moved down to increase the volume, or what we call it the displacement volume. So this one we call it intake stroke. Then it will be moved to the compression stroke, while the piston will be pushed to the top maximum or the top dead center, while the both valves it will be closed. Here in this part, we have increased the pressure, we have increased the temperature, which is reached to point number 2. In the first part, we have atmospheric pressure because the inlet, the intake valve that will be opened, that will allow the atmospheric pressure to be moved inside the whole system. So once it will be closed, it will reach to the piston will be moved to the bottom part. So at this location, the piston have been moved from the top dead center to the bottom dead center. Then at point number 2, which is the compression, then we are compressing everything. That's why we are increasing the pressure and the temperature, while the piston will be moved from the bottom dead center to the top dead center. At point number 3, we will get the ignition from the spark. So at this part, we are increasing the pressure and the temperature. Maybe the temperature could be reached to 700 Celsius, or maybe it reach maybe more than this amount. So at this location, the temperature and the pressure will be the maximum. So by applying the spark, the the whole gasoline will be getting the explosion. So it will force the piston to be pushed down to the bottom dead center at this time when we rotate the crankshaft. Then at this part we will have the whole smoke that we need to release it to the exhaust. So we need to open the exhaust valve. Then the piston will be pushed to the top dead center. So at this part, we have isoentropy in two locations between point number 1 and point number 2, and between point number 3 and point number 4. So we have heat inlet between point 2 and point number 3. Then we have heat outlet between point number 4 and point number 1. We need to release back to the first location. So at this part, we will have the work net that happening in the whole system. So usually we have 4-stroke cycle and 2-stroke cycle, and this is the diagram or the video, small short video that will help us to understand how the fuel is moving inside the whole system. So we may have intake valve from the side valve, not the top valve as the previous explanation. So from the side valve, we are allowed the fuel to be moved inside the system. Then it will reach to the combustion area. In this combustion area, we are compressing the whole gasoline by pushing up the piston. Then we will get the spark to release the whole, to make the combustion and release the whole gasoline or the smoke to the outside. So in the 4-stroke, we have one cycle, which is covering by 4-stroke as explained earlier. Then we'll have 2 revolutions, 2 move up and 2 move down. Then the other part, we have 2-stroke. Then it will be one cycle. We have 2-stroke, which is 2 pistons push up and 2 pistons push down together. Then we have 1 revolution. So in the Otto cycle, based on the PV diagram and TS diagram we have explained just earlier, just now. So between point number 1 and point number 2, we have isentropic compression, and between point number 2 and point number 3, we have constant volume heat addition. Then between point number 3 and point number 4, we have isentropic expansion as we explained earlier. Then between point number 4 and point number 1, we have volume heat rejection. So at this part, we have the entropy between point number 1 and point number 2, it will be a constant, and between number 3 and point number 4, it will be constant, while between point number 4 and point number 1, we have volume is a constant, and between number 2 and point number 3, we have volume as constant. So the most important formula that we have to keep in our mind in our solution, that we have heat in and negative with heat out plus the W in negative with W out. It will be equals the differential of the enthalpy between exit and the inlet. While the heat inlet, it will be calculating by the internal energies between number 3 and point number 2, as explained earlier in the previous slide. Then it will be equal the constant volume multiplied by the differential of the temperature. And the heat out between point number 4 and point number 1, then it will be the constant volume multiplied by the differential of temperature between number 4 and number 1. So the efficiency of the Otto cycle we have explained earlier in the beginning, that we have mentioned the W net over the heat in, which is equals 1 negative with the Q out and so on based on the formula that we have explained just now. So also that we have to find the rest of the process between point number 1, point number 2, and point number 3 and point number 4, which is isoentropic. So the relationship between both of them will be based on the temperature or the ratio of the temperature and the ratio of the specific volume. So temperature number 1 over temperature number 2, it will be equals the specific volume of point number 2 over the specific volume number 1. And these two data with that we need to find it from the table that we are having from the beginning of this course. So it will be powered by k negative with 1. Usually k here is a constant that it will be equals 1.35, and it sometimes will be calculated based on 1.4. And this k I will provide for you in the question. In case it will be not provided, so you may need to calculate it as 1.42 for easy calculation. So it will be also specific volume point number 3 over specific volume number 4, which is for k negative with 1, it will be equal to the temperature number 4 over temperature number 3. So the efficiency of the Otto cycle will be equals 1 negative with 1 over R, which is the compression ratio, power the K negative with 1. While R here is the compression ratio we have explained earlier between the volume maximum over volume minimum, or the specific volume 1 over specific volume number 2. K from the formula to be equal Cp over Cv, while as I mentioned just now, it will be provided in the question. So, according to the spark ignition engine, the compression ratio it was limited to the Otto engine, or according to the engine knocking. The knocking it will be usually we are hearing in the car when it's moving by getting the not proper fuel or not proper gearbox, that it will be getting some knocking. And this knocking it will be cannot relate it because it's reducing engine performance and the damage when the engine is up. So example number 1 is mentioning an ideal Otto cycle has been compression ratio is equals 8. At the beginning of the compression process, air is at 100 kilopascal, which is atmospheric pressure, and 17 Celsius, which is this usually at point number 1. So, and 800 kilojoule per kilogram is the heat transferred to the air during the constant volume in additional process. Accounting for the variation of specific heats, air temperature determine the point number 1, the maximum temperature and the pressure occur during the cycle. Then point number 2, which is the net output, then the thermal efficiency, and the last part, which is the mean effective pressure of the cycle. So usually with the point number 1, we are going to the table because we have air, so we are going to table number 17 to calculate to find the internal energy and the relative specific volume. So from these two parameters, we will be able to find the relative specific volume number 2. Then we'll be able to calculate it based on the compression ratio. According to this kind of the calculation, we'll be able to calculate temperature number 2 from the table as well. Then we will find the internal energy of point number 2. Based on the ratio that we have found it in chapter number 5, which is related to the pressure multiplied specific volume over temperature, same between point number 2 and point number 1, we'll be able to calculate pressure number 2. Then the heat N, it will be based on the differential of the internal energies point number 2 and point number 3. We'll be able to calculate the internal energy point number 3 to find the temperature number 3 and the relative specific volume number 3. Same from the same ratio, we'll be able to calculate the pressure number 3. Then at point number at B, we need to calculate the work net. Then we will need to calculate the heat in and heat out. So based on this calculation, we have calculated already heat in. So we need to calculate heat out based on the internal energy between 4 and 1. So we'll be able to calculate the work net. The other part, we need to calculate the efficiency of the W net over heat, and then